Hello, myself Dr. B.Z.D. Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about instruction pipelining. At the end of this video, the student will gain knowledge regarding what is instruction pipelining, what are the steps for execution of the instruction, and how the operations of instruction pipeline can be carried out, and the conflicts while executing this instruction pipelining. So this topic learning outcome will be mapped to the course outcome of summarize the concept of pipelining and inter-process communication for advanced processor design. So the basic concept that can be discussed in this video are introduction, what are the steps of instruction pipelining, what is RISC pipelining, and the examples. So here, during parallel processing or parallel computers, for the most recent multiprocessors can support the parallel processing. So nowadays, almost all are engineering and scientific applications, and the applications can be varying according to the cutting edge technologies like the artificial intelligence, machine learning, big data, blockchain. So all these are very computational incentive, and they require a large volume of data processing. So to support these, advanced processors can be designed that can support the parallel processing. That means more than one instruction can be executed simultaneously. So with the help of this parallel processing system, the number of instructions that can be executed per unit of time can be increased, which in turn results in increase of the throughput as well as performance of the system. So these computational incentive applications may require the parallel processing capabilities. This parallel processing can be implemented with the help of employing multiple functional units in the computer. Generally, the basic functional unit, the processing, the CPU input and output unit, the CPU can provide the arithmetic and logical processing capability for the applications. So a single ALU cannot be enough to provide these engineering and scientific applications. That's why multiple functional units employed in these parallel processing systems. So here each functional unit can have one dedicated functionality to perform the task. For example, to perform a fixed point arithmetic, some functional units can be employed, and for logical implementation, for shift operation implementation, for floating point arithmetic, the separate functional units can be employed. So this is the one way to achieve the parallel processing. The second method is with the help of pipelining, the parallel processing capabilities can be supported. So what is pipelining means? Pipelining processing is an implementation technique where the arithmetic sub-operations are the phases of the instruction cycle can overlap in execution. That means multiple operations, sub-operations can be executed in a parallelly with the help of pipeline process. That can be any arithmetic operation, or this pipelining concept can be implemented for the execution of the phases or steps of the instruction cycle. So it is a technique of decomposing the sequential process into sub-operations, each sub-operation being executed in a specialized dedicated segments and can be operated in parallel with the other segments of the pipeline. So a pipeline can be visualized as a collection of processing segments through which binary information flows. So the segments can execute or implement parallelly so that the data can be flow in between these segments concurrently. So the way of speeding up execution of instruction is the pipelining concept. So here, as a summary, the pipeline can be termed as the overlap execution of multiple instructions. So the key idea of pipeline is breaking big computational task into small pieces, and each piece can be referred as the segment. These separate each piece with a pipeline register, and this segment can be implemented in a dedicated pipeline registers. So it is faster for repeated computations. So repeated sub-operation can be implemented with the help of the pipeline concept, and this definitely increases the throughput or performance of the computer, but it requires some hardware complexity, so the cost of the computer can be increased with the special functional units. And how pipeline can be implemented, we will consider with an example. So here take one arithmetic task, that is A into B plus C, and this operation can be repeated for the numbers 1, 2, 3 until 7. So the repetition computations can be easily implemented with the help of pipeline. So here the major task can be subdivided into segments. So the major computational task here is two numbers can be multiplied and the product can be added to the third number. So this task can be divided into three subtasks. That is segment 1. The segment 1 can be used to give input to the A and B values, and these A and B can be stored in the corresponding registers R1 and R2. In the second segment, the values that is loaded in the registers R1 and R2 can be multiplied, and the C value can be loaded into the R4 register. This is the second segment operation. And the third segment operation is adding to this product that is available in the register R3 with the register R4 value. So these are the three segments. The major task of A into B plus C can be divided into segment 1, segment 2 and segment 3. And how the pipelining process can be carried out. So here the values can be loaded in these registers and can be multiplied with the multiplexer. So here at the segment 1, the values can be loaded into the corresponding registers of register R1 and R2. In the segment 2, the multiplication can be performed, and this multiplier or the product value can be stored in the register R3. At the same time, the C value can be loaded to the R4. So this can be the segment 2 operation. And after getting this product R3 and this R4 can be added, and the result is stored in the register R5. This is the segment 3 operation. In this way, the segments can operate or implement simultaneously in the pipelining process. So here, during each clock pulse, how these segments can be implemented. During first clock pulse, the segment 1 can be implemented, that is inputting R1 and R2. So A1 and B1 can be loaded to the registers R1 and R2. And in the second clock pulse, these first numbers that are loaded in the register can move to the execution of the segment 2, so that the product of A1 B1 can be carried out, and at the same time the C value can be loaded into the R4, and the second numbers can be loaded. The segment 1 of the second instruction can be loaded. the A2 and B2 values to the R1 and R2 registers. And in the third clock pulse, the segment 2 of the first instruction can be moved to the implementation towards the segment 3. So there the product can be added with the C value so that instruction execution can be completed. So 3 clock pulses can be required to execute one instruction. So at the third clock tick, the instruction 1 is completed its execution, instruction 2 at the execution of the segment 2, and instruction 3 at the execution of segment 1. So thereby the number of instructions that can be executed per unit of time can be increased, which in turn increases the throughput of the computer. And here there are two types of pipelining. One is arithmetic pipeline, second one is instruction pipeline. Arithmetic pipeline majorly used to implement high-speed computers to perform the arithmetic capabilities. So the arithmetic task that is processed by the computer can be divided into sub-operations or the segments. Just we discussed the example A into B plus C. So the task can be divided into 3 sub-segments. There each segment can be operated concurrently. So they are used to implement floating point operations, multiplication of fixed point numbers, and similar computations encoded in scientific problems. Generally, the parallel processing systems can be used to support the engineering and scientific applications where computational incentive and data processing intensive applications can require these type of computers. So these type of applications generally involved in the complex arithmetic operations like floating point operations as well as multiplication of fixed point numbers. So these operations can be easily implemented with the help of arithmetic pipelining. So an arithmetic pipeline divides an arithmetic problem into various subproblems for execution in various pipeline segments. Just we discussed that A into B plus C. So here A into B loading of the registers can be the first segment and product and loading of C value to the registers is the second segment, and third segment can produce the addition of these values. So like this the complex task can be divided into parts and this can be referred as the segment. The segments can be executed in the pipeline registers in a dedicated fashion with in parallel to the other segments of the pipeline. So that is the arithmetic pipeline. The second variety is the instruction pipeline. What is instruction pipeline? An instruction pipeline reads consecutive instructions from memory while in other segments the previous instructions are being implemented. So here the instruction cycle can has steps during the instruction execution. Whenever the instruction is fetched and it can be stored in the instruction register, it can be represented in the instruction format. The instruction format generally specifies the address, the opcode and the mode. So here the mode can be direct addressing mode or indirect addressing mode. Depending upon the opcode, the type of the instruction can be determined. So here 3 types of instructions are available. Arithmetic memory referenced instruction, register referenced instruction and IO referenced instructions. So the opcode specifies what operation to be performed and the address is specified the operand where it is located with the help of the mode bit of the instruction. So here this operation is generally referred as the fetch step of the instruction. After this, the opcode can be decoded. So during decode, it has to specify and identify what type of instruction it is. Next, depending upon the mode, the operand can be fetched from the memory, and the last step can be the operation, what operation to be performed can be identified, and operand can also be available. So the execution of the instruction can be carried out. So in the instruction pipeline, these steps can be executed in a overlapped fashion with other instructions. So multiple instructions can be be overlapped or concurrently executed with the help of instruction pipeline. So pipeline processing can occur not only in the data stream but in the instruction stream with the help of the instruction pipeline. So most of the digital computers with complex instructions require instruction pipeline to carry out operations like fetch, decode and execute the instructions. So what are the general steps that can be considered in the instruction cycle? The first one is fetch instruction from the memory. So from the location of the memory, the instruction can be retrieved and stored in the instruction register during this step. Next, decode the instruction means the opcode can be decoded and identify the type of instruction, whether it is memory referenced or register referenced or IO instruction. The third one is calculate the effective address. In this step, the operand where it is located in the memory, either direct addressing or the indirect addressing. In case of direct addressing, in the instruction register, what address specified, at that address only the operand can be available. But case of indirect addressing, the address specified in the instruction register can specify the effective address. So 2 clock cycles can be required to retrieve the operand in case of indirect addressing mode. So calculating the effective address with the help of various addressing modes is the third step. Next, fetch the operands from the memory so that they are readily available to implement the operation. So that execute the instruction and store results in the proper place. So these are the 6 steps that can be used during the instruction cycle. So with multiple segments can take place different time duration to work on the incoming data. So this can be avoid the instruction pipeline from working at its maximum speed. So there is an optimization can be required so that the steps of the instruction cycle can be reduced to increase the computational speed of the computer. So the organization of instruction pipeline will be more efficient if the instruction cycle is divided into segments of equal duration. So one of the most common example for this type of organization is 4-segment instruction pipeline. So here in the previously it is having the 6 steps. If you reduced this instruction cycle into the 4 steps, which can be carried out in the 4-segment pipeline, so it is an optimized way of executing the instructions. What is this 4-segment instruction pipeline? A 4-segment instruction pipeline combines 2 or more different segments and make it as a single one, so that the 6-segment instruction cycle can be reduced into the 4. For example, the decoding of the instruction can be combined with the calculation of effective address into 1 segment. So 2 steps can be combined here in order to optimize the execution of the instruction cycle. So that the 4-segment instruction cycle, the segment 1 is fetch the instruction from the memory. The second segment is decode instruction and calculate effective address. So the step 2 and step 3 are combined here. And the segment 3 is fetch operand from the memory Fourth step is executing the instruction and storing the result. So that the 6 steps can be reduced into the 4 steps, and each step carried out in a separate dedicated segment in the instruction pipelining. What are the factors that can be considered for the instruction pipelining? The first factor is overhead in each stage of pipeline for data movements buffer to buffer. So how the data can be flowed and how operand can be available, that conflicts of data dependency is the one of the factor that can be considered. Next, amount of control logic needed to handle the memory and register. So concurrent execution needs the complex operation so that the control logic can be effectively designed to handle these conflicts. Dependencies increases with size of pipeline. So if more segments are present, the data dependency can be increased. Why? Because these segments can be implemented parallelly. It needs time for buffer to operate. So here during branching, and if the data that is needed for execution of segment is not available, a delay has to be caused until the needed data can be available. So it needs time for buffers to operate. So these factors can be considered during the instruction pipeline. So what is the segment of operations that can be performed during the instruction pipeline? During segment 1, the segment 1 can be referred as F5, so that the fetch segment can be executed using first in first out basis buffer, and the instruction from the memory can be fetched and stored in the instruction register. The second segment is DA, can be referred as DA. The instruction fetched from the memory is decoded in the second segment. The decode operation can be performed. The effective address is computed in an independent arithmetic circuit. So where the operand is available, whether it is direct or indirect, or depending upon various addressing modes, the effective address of the operand can be calculated in the second segment, and it can be referred as DA. And the third segment is the F4. So an operand from the memory is fetched in the third segment, and the fourth segment can be referred as EX. So here the operands can be available, and what operation to be performed, that can be decided in the decoded. So the instruction execution can be carried out. The instructions are finally implemented in final segment of the pipeline organization, and that segment can be referred as EX. So the fourth segment can be referred as F5, fetching the instruction, DA, decoding the instruction and calculation of effective address of the operand, F4, fetch the operand, EX, execute the instruction. So this is the instruction pipeline process. Fetch instruction from the memory. This is the segment 1. So here the instruction from the memory location can be fetched and stored in the instruction register. This is the second segment, decode instruction and calculate the effective address depending upon the address mode of the instruction. That is the second segment. After decoding, whether it is a branching instruction. Why? Because the branching instruction can alter the execution sequence of the program conditionally or unconditionally. If it all branching occurs, the CPU can stop the current program execution and move to the branch location and execute those programs. And after completion of this, then it has to return to the main program execution. To do this, the PC value can be, the return address has to be saved so that updation in the PC can be required. So after decoding, the type of instruction can be decided, and whether it is a branch instruction or not branching instruction can be decided. If at all it is a branching instruction, updation of PC value can be done so that the program can move to the specific location for execution, and the return address can be stored in the stack, so that emptying the pipe, so that the current instruction execution can be temporarily suspended. So if it are not branch, then fetch operand from the memory, the third segment of operation can be carried out. After that, execute the instruction. At the end of instruction cycle, whether there is an interrupt arises or not can be checked. So here interrupt can be arised or not can be checked. If it all interrupt occurs, the computer can stop the current program execution temporarily and service the interrupt service routine. Later on it has to resume the main instruction execution. So if it all interrupt occurs, then interrupt handling can be performed and update the PC value, empty the pipe. If at all no interrupt is there, next instruction can be fetched from the memory. In this way, the instruction pipeline process, the 4 segments can be used. So here after decoding, the branch instruction is occurred or not, and after execution of each instruction cycle, interrupt is arised or not can be checked. So what is the timing diagram of instruction pipeline? So during first clock step, the fetch of instruction can be carried out. During second clock tick, the decoding of instruction, first instruction can be, the first instruction can be moved to the second segment so that the decoding operation can be performed. At the same time, the second instruction, fetch instruction, parallelly the second instruction can be moved to the segment 1. At the third clock tick, the first instruction moved to the fetch the operand stage, the third step, and second instruction moved to the decoding segment stage, and third instruction is initialized with the fetch instruction, the segment 1 operation. So parallelly here 3 instructions are executing, and in the fourth step the execution of first instruction can be completed. So 4 clock cycles can be required to complete the first instruction. At the same time of fourth clock tick, the first instruction execution is performing, and second instruction is at third segment fetch the operand state, and the third instruction is at the second segment decoding of the instruction and calculating the effective address stage, and the fourth instruction is at segment 1 of fetch instruction. In this way, concurrently the segments can perform the various operations in the instruction pipeline, the steps of the instruction execution cycle. So in case if it all branch occurs, how the timing diagram can be. So the first instruction can be executed in the first cycle. Next, how the first instruction is carried out in the successive cycles. If the after the fetching the instruction, if it all decoding operation of the third instruction, after decoding it is branch instruction or not can be verified. So here if it all branch instruction, empty the, update the PC value, empty the pipe. So the third instruction pipe can be emptied here. If in case of the branch instruction can be occurred. Why? Because the branch instruction can alter the execution sequence of the program. So in this way, the steps of the instruction cycle can be executed in a parallel with the help of instruction pipeline, so that the performance of the computer can be greatly increased. What is RISC pipelining? RISC stands for Reduced Instruction Set Computer. Okay, so here in the instruction pipeline, the steps of the instruction cycle can be optimized to improve the performance. But each processor can have instruction set architecture which can support variety of instructions like data transfer instruction, data manipulation instructions, and program control instructions. So the number of instructions available in the instruction set architecture can be reduced to improve the performance with the help of RISC, reduced instruction set computer. So it is introduced to execute as fast as one instruction per clock cycle. So here in the previous example, 4 clock cycles are required for execution of a single instruction. But with the RISC, only the instruction can be executed with a single clock cycle. So this RISC pipeline helps to simplify the computer architecture design. So the method to obtain the implementation of an instruction per clock cycle is initiate each instruction with each clock cycle and to pipeline the processor to manage the objective of single cycle instruction execution so that the performance of the computer can be increased or optimized with the help of RISC pipelining. One instruction per clock cycle can be executed with the help of RISC pipelining. What are the principles of RISC pipelining in order to support single cycle instruction? So keep the most frequently accessed operands in the CPU registers. So cache has to be maintained so that most frequently used data items for the processing can be stored in the processor registers. Next principle is it can minimize the register to memory operations. So the data is readily available in the CPU registers. Next, it can use a high number of registers to enhance operand referencing and decrease the processor memory traffic. So memory referencing can be greatly reduced so that more number of general purpose registers can be available so that the operands can be stored in these large number of registers. It can optimize the design of instruction pipeline such that the number of compiler code generation can be achieved. So here it can simplify the instruction set and lay out those complex and unnecessary instructions. So instruction set architecture, the type of instructions can be greatly reduced and unnecessarily instructions that can cause the processor and memory traffic can be avoided in case of the RISC pipelining. So with the RISC architecture, we can go for single or 3-segment instruction pipeline can also be possible. The 6 steps can be reduced as 4 by using the instruction pipeline. So with the RISC, we can reduce into 3 also. So which shows how a compiler can optimize the machine language program to compensate for the pipeline concept. The 3 segments are, the first one is I, instruction fetch, A, ALU operation, which can you consider the decoding of instruction as well as calculation of effective address and fetching the operands. Next, execute the instruction. So these are the 3-segment instruction pipeline. So that here the instructions can be carried out and can be completed in a 3 cycles, IAE, the 3 segment of operations. So if it all a delayed load, no operation has to be taken place to resolve the conflict of the data dependency. Now we have to discuss about what are the conflicts that can be arised in the pipelining. The difficulties that can be arised during pipeline instructions are categorized into resource conflicts, data dependency conflicts, and branch difficulties. What are the resource difficulties? So, these difficulty or conflict can arise when 2 segments are access the memory at the same time. So if the processor to memory referenced instructions, when two segments can has to point to the same memory location, then this resource conflict can be arises. So this problem can be resolved by employing instruction and data memories separately. So this can be done in case of RISC pipelining to optimize the instruction execution time. Second one is data dependency. Data dependency occur when an instruction depends on the result of a previous instruction but it is not available. So the data that is required for segment execution that is used by the another segment. So this type of data dependency problem can arise. The operand access to memory is delayed until required data is available. So these the techniques that can be used to resolve this problem are hardware interlock, operand forwarding, delayed load. What is hardware interlock means? A special lock mechanism with the help of hardware can be provided so that the data items that are required for execution of instruction can be locked. Okay. Operand forwarding means the data dependency identification hardware circuitry can identify the conflicts of the data dependency and the operand required can has to be forwarded for smooth execution of the instruction. Delayed load means the data that is required for execution of the segment can be supplied or it has to wait until the data can be available. So these are the three techniques that can be used to resolve the data dependency conflict. The third one is branch difficulties. So these difficulties can be arises from branch instructions or the instructions that modify the value of the PC. So whenever during branch occur, the PC value can be updated and empty a pipe can be taken place in order to alter the sequence of execution of the program. And the techniques that handle this branch instructions is prefetch the target instruction. So the target instruction address location can be stored in the special buffer and can be supplied during the execution of the instruction. Second technique is branch target buffer. So BTB is a special buffer which is used to store the updated PC value so that the return address can be easily taken and the instruction can be quickly executed. And third one is loop buffer. So the special hardware buffer that is used to store the return address of the instruction in case of the buffer. The third technique for the branch difficulties is the loop buffer. The loop buffer is used the special hardware mechanism which is used to store the return address of the instruction execution in case of branch occur. The next method is branch prediction. So with the help of hardware circuitry, the branch occurrence can be predicted so that the program sequence can be altered safely so that the updated PC value can be stored and can be supplied for the instruction execution. Delayed branch. In this also special hardware mechanism can be used to identify the branch occurrence and the instructions execution can be waited until the return address can be available. So these are the techniques that can be used to avoid the branch difficulties. So these are the references used in this video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.